In this tutorial, we'll explain how persistent volume and persistent volume claim resources can be used together to link various storage architectures to applications running in your cluster. Let's get started. You might remember from our previous tutorial that Kubernetes supports a wide variety of volume plugins for both stateless and stateful apps. Non-persistent volumes like config map are firmly linked to the pod's lifecycle. They are detached and deleted after the pod is terminated. However, with stateful applications like databases, we want to have volumes that persist data beyond the pod's lifecycle. Kubernetes solves this problem by introducing the persistent volume and persistent volume claim resources that enable native and external persistent storage in your Kubernetes clusters. So why do we need to use a persistent volume resource in Kubernetes? Well, on the one hand, we have different storage infrastructures such as Amazon EBS, GCE persistent disk, or Gluster FS, all of which have their own specific storage type, architecture, and API. If we were to attach these diverse storage types manually, we would have to develop custom plugins to interact with the external drive's API, such as mounting the disk, requesting capacity, managing the disk's lifecycle, etc. We would also need to configure a cloud storage environment, all of which would result in unnecessary overhead. Fortunately, the Kubernetes platform simplifies storage management for you. Its persistent volume subsystem is designed to solve the problem we just described by providing APIs that abstract details of the underlying storage infrastructure, for example, AWS, EBS, Azure Disk, etc. This allows users and admins to focus on storage capacity and storage types their applications will consume rather than the subtle details of each storage provider's API. PVs provide the right amount of resources for your pods regardless of your choice of storage provider. Linking a persistent volume to your application involves several steps: provisioning a PV, requesting storage, and using the PV in your pod or deployment. Let's discuss these steps. Kubernetes users need to define a persistent volume resource object that specifies the storage type and storage capacity, volume access modes, mount options, and other relevant storage details. Once the PV is created, we have a working API abstraction that tells Kubernetes how to interact with the underlying storage provider using its Kubernetes Volume plugin. Kubernetes supports static and dynamic provisioning of PVs. In the static provisioning, PVs are created by the cluster administrator and are allowed to use actual storage available in the cluster. This means that in order to use static provisioning, one needs to have a storage capacity provision beforehand, such as Amazon EBS. On the other hand, a dynamic provisioning of volumes can be triggered when a volume type claimed by the user does not match any PVs available in the cluster. For dynamic provisioning to happen, the cluster administrator needs to enable the default storage class admission plugin that defines default storage classes for applications. To make PVs available to pods in the Kubernetes cluster, you should explicitly claim them using the persistent volume claim resource. A PVC is bound to the PV that matches storage type, capacity, and other requirements specified in the claim. Binding the PVC to the PV is secured by the control loop that watches for the new PVCs and finds a matching PV. The claim will be automatically unbound if a matching volume does not exist. For example, if the PVC is requesting 15 gigabytes and there are two PVs in the cluster, one with 20 gigabytes and the other with 10 gigabytes, the PVC will be bound to the PV with 20 gigabytes. In the example shown here, the PVC will be bound to the persistent volume 1 and not the persistent volume 2 because the PVC's resource request and the volume mode match the first volume only. Pods can use PVs by specifying a PVC that matches its resource and volume options definitions. This works as follows. When the PVC is specified, the cluster finds the claim in the pod's namespace, uses it to get the PV backing the claim, and mounts the corresponding volume into the containers in the pod. Note that the PVCs should be referenced as volumes in a pod spec. For example, here we see a pod spec that uses a persistent volume claim named test claim, referring to some PV. There's a number of persistent storage volume plugins that can be used by PVs and PVCs. For simplicity, we've put them into a table. You can take a closer look at this table by viewing our blog post, Persistent Storage with Persistent Volumes in Kubernetes, on supergiant.io. Now, let's discuss how PVs actually work. First, PVs are defined as Kubernetes API objects with a spec and a list of parameters. This is an example of a typical persistent volume definition in Kubernetes. As you can see here, we have defined a PV for the NFS volume type. Key parameters defined in this spec are the following. Spec capacity, storage capacity of the PV. In this example, our PV has a capacity of 10 gigabytes. The capacity property uses the same units as defined in the Kubernetes resource model. It allows users to represent storage as unadorned integers or as fixed point integer with one of these SI suffixes or as their binary equivalents. Currently, Kubernetes users can only request storage size. However, future attributes may include throughput, IOPS, etc. Spec volume mode available since Kubernetes version 1.9. The volume mode property supports raw block devices and file systems. Block storage mode offers a raw, unformatted block storage that avoids file system overhead and hence ensures lower latency and higher throughput for mission-critical applications, such as databases and object stores. Valid values for this field include file system, the default, and block. Spec access modes defines how the volume can be accessed. Note that valid values vary across persistent storage providers. In general, the supported field values are read-write once. The volume can be mounted as a read-write volume only by a single node. Read-only many. Many nodes can mount the volume as read-only. Read-write many. Many nodes can mount the volume as read-write. A volume can only be mounted with one access mode at a time, even if it supports many. Spec storage class name. A storage class of the volume defined by the storage class resource. A PV of a given class can only be bound to PVCs requesting that class. A PV with no storage class name defined can only be bound to PVCs that request no particular class. Spec persistent volume reclaim policy. A reclaim policy for the volume. Right now, Kubernetes supports the following reclaim policies. Retain. If this policy is enabled, the PV will continue to exist even after the PVC is deleted, but it won't be available to another claim until the previous claimant's data remains on the volume and PV are deleted manually. Recycle. This reclaim policy performs a basic scrub operation on a given volume and makes it available again for a new claim. Delete. This reclaim policy deletes the persistent volume object from the Kubernetes API and associated storage capacity in the external infrastructure, for example, AWS, EBS, Google Persistent Disk, etc. Spec mount options. A K8s administrator can use this field to specify additional mount options supported by the storage provider. In the spec shown here, we mount an NFS hard drive and specify that the NFS version 4.2 should be used. Just a note that not all providers support mount options. For more information, see the official documentation on Kubernetes. Spec NFS is the list of NFS-specific options. Here we say that NFS volume should be mounted at the TMP path of a server with the IP shown here. As we've already mentioned, persistent volume claims must be defined to claim resources of a given PV. Similar to PVs, PVCs are defined as Kubernetes API resource objects. Let's see an example. This PVC targets volumes that have read-write-many access mode. It requests the storage only from volumes that have block volume mode enabled, and claims 10 gigabytes of storage from any matching PV. It also filters volumes that match a slow storage class and specifies a label selector to further filter a set of volumes. Only volumes with a label stable can be bound to this claim. This PVC matches the storage class of the PV defined here. However, it does not match the volume mode and access mode in that PV. Therefore, our PVC cannot be used to claim resources from the PV NFS PV. Once the PV and PVC are created, using persistent storage in a pod becomes straightforward. In this pod spec, we pull Apache HTTP server from the Docker Hub repository. We define a volume test PV and use the PVC volume claim to claim some PV that matches this claim. And we mount the volume in the container. That's it. You should now understand the theory behind PVs and PVCs and key options and parameters available to these API resources. Let's consolidate this knowledge with a tutorial. In this tutorial, we'll create a persistent volume using HostPath Volume plugin and claim it for the use in the deployment running Apache HTTP servers. HostPath volumes use a file or directory on the node and are suitable for development and testing purposes. Please note that HostPath volumes have certain limitations. It's not recommended to use them in production. Also, in order for the host path to work, we will need to run a single node cluster. See the official documentation for more information. To complete this example, we use the following prerequisites: a Kubernetes cluster deployed with Minikube, and a kubectl command line tool installed and configured to communicate with the cluster. First, let's create a directory on your node that will be used by the host path volume. This directory will be a web root of Apache HTTP server. You need to open a shell to the node in the cluster. Since you are using Minikube, open a shell by running minikube ssh. In your shell, create a new directory. Use any directory that does not need root permissions. Then create the index.html file in this directory containing a custom greeting from the server. Use the directory you created. The next thing we need to do is create a host path persistent volume that will be using this directory. This spec defines a PV named PV-local with a 10 GB capacity. It sets the PV's access mode to read-write once, which allows the volume to be mounted as read-write by a single node. It assigns a storage class named local to the persistent volume. It configures hostpath volume plugin to mount local directory at home username data. Save this spec in the file and create the PV running the following command. Let's check whether our persistent volume was created. This response indicates that the volume is already available but still does not have any claim bound to it. So let's create one. The next thing we need to do is to claim our PV using a persistent volume claim. Using this claim, we can request resources from the volume and make them available to our future pods. Our PVC does the following: filters the volumes labeled local to bind our specific host path volume and other host path volumes that might be created later. Targets host path volumes that have read-write once access mode. Requests a volume of at least 5 GB. First, save this resource definition in the host path PVC YAML, and then create it similar to what we did with the PV. Let's check the claim running the following command. The response should be something like this. As you can see, our PVC was already bound to the volume of the matching type. Let's verify that the PV we created was actually selected by the claim. The response should be something like this. Did you notice the difference from the previous status of our PV? You'll see that it is now bound by the claim host path PVC that we just created. The claim is living in the default Kubernetes namespace. That's exactly what we wanted to achieve. Now everything is ready for the use of your host path PV in any pod or deployment of your choice. To do this, we need to create a deployment with a PVC referring to the host path volume. Since we created a PV that mounts a directory with the index.html file, let's deploy Apache HTTP server from the Docker Hub repository. As you see, along with the standard deployment parameters like container image and container port, we have also defined a volume named web that uses our persistent volume claim. This volume will be mounted with our custom index.html at this path, which is the default web root directory of Apache HTTP for this Docker Hub image. Also, deployment will have access to 5 GB of data in the host path volume. Save this spec and create the deployment using the following command. Let's check the deployment's details. Along with other details, the output shows that the directory was mounted from the web RW volume and that our persistent volume claim was used to provision the storage. Now let's verify that our Apache HTTP pods actually serve the index.html file that we created in the first step. To do this, let's first find the UID of one of the pods and get a shell to the Apache server container running in this pod. We'll enter your pod using the following command. Now we're inside the Apache 2 containers file system. You may verify this by using Linux's ls command. The image uses Linux environment so we can easily install curl to access our server. When the curl is installed, let's send a GET request to our server listening on localhost 80. Remember that containers within a pod communicate via localhost. That's it. Now you know how to define a PV and a PVC for host path volumes and use this storage type in your Kubernetes deployments. This tutorial demonstrated how both PV and PVC take care of the underlying storage infrastructure and file system, so users can focus on just how much storage they need for their deployment. This tutorial is over, so let's clean up after ourselves. Delete the deployment, delete the PV, delete the PVC.
Finally, don't forget to delete all files and folders, PV and PVC resource definition files that we created.
We hope you have a better understanding of how to create stateful applications in Kubernetes using persistent volume and persistent volume claim. If you're interested in learning more about Kubernetes, visit the supergiant.io website where we've published valuable resources on our website and blog. Thanks for watching.